Let's talk about how to handle a horizontally launched projectile problem. These, technically speaking, if you already know how to do projectile problems, there's nothing new except that there's one aspect to these problems that people get stumped by all the time. So I'm going to show you what that is in a minute so that you don't fall into the same trap. What we mean by a horizontally launched projectile is any object that gets launched in a completely horizontal velocity to start with. So if something is launched off of a cliff, let's say, in this straight horizontal direction with no vertical component to start with, then it's a horizontally launched projectile. What could that be? I mean, a boring example is just a ball rolling off of a table. If you just rolled a ball off of a table, then the velocity the ball has to start off with, if the table's flat and horizontal, the velocity of the ball initially would just be horizontal. So if the initial velocity of the object for a projectile is completely horizontal, then that object is a horizontally launched projectile. A more exciting example, people do crazy stuff. Let's say this person's going to cliff dive or base jump, and they're going to be like, whoa, let's do this. We're going to do this. They're pumped up. They're going to run, but they don't jump off the cliff. They just run straight off of the cliff because they're kind of nervous. Let's say they run off of this cliff with 5 meters per second of initial velocity, straight off the cliff. And let's say they're completely crazy. Let's say this cliff is 30 meters tall. So that's like over 90 feet. That is kind of crazy. So 30 meters tall, they launch, they fly through the air. There's water down here, so they initially went this way, and they start to fall down, and they do something like, and then they splash into the water. Hopefully they don't hit any boats or fish down here. That fish already looks like he got hit, he or she. All right, fish over here, person splashes in the water. We want to know, here's a question you might get asked, how far did this person go horizontally before striking the water? This is a classic problem. It gets asked all the time. And if you were a cliff diver, I mean, don't try this at home, but if you were a professional cliff diver, you might want to know, for this cliff height and this speed, how fast do I have to run in order to avoid maybe the rocky shore right here that you might want to avoid? Maybe there's this nasty, craggy cliff bottom here that you can't fall on. So how fast would I have to run in order to make it past that? All right, so conceptually what's happening here, same thing that happens for any projectile problem, the horizontal direction is happening independently of the vertical direction. And what I mean by that is that the horizontal velocity evolves independent to the vertical velocity. Let me give the velocity this color. So say the vertical velocity, or the vertical direction is pink, horizontal direction is green. This vertical velocity is going to be changing, but this horizontal velocity is just going to remain the same. These do not influence each other. In other words, this horizontal velocity started at 5. The person's always going to have 5 meters per second of horizontal velocity. So this horizontal velocity is always going to be 5 meters per second the whole trip, assuming this person really is a freely flying projectile, assuming that there was no jetpack that propelled them forward or no air resistance. This person's always going to have 5 meters per second of horizontal velocity up until the point right when they splash into the water. And then at that point, there's forces from the water that influence this acceleration in various ways that we're not going to consider. How about vertically? Vertically, this person starts with no initial velocity. So this person just ran horizontally straight off the cliff, and then they start to gain velocity. So they're going to gain vertical velocity downward, and maybe more vertical velocity because gravity keeps pulling, and then even more. This might go off the screen, but it's going to be really big. So a lot of vertical velocity. This should keep getting bigger and bigger and bigger because gravity is influencing this vertical direction, but not the horizontal direction. So how do we solve this with math? Let's write down what we know. What we know is that horizontally, this person started off with an initial velocity. V initial in the x, I could have wrote I for initial, but I wrote 0 for V not in the x. It still means initial velocity is 5 meters per second. And we don't know anything else in the x direction. You might think 30 meters is the displacement in the x direction, but that's a vertical distance. This is not telling us anything about this horizontal distance. This horizontal distance or displacement is what we want to know. This horizontal displacement in the x direction, that's what we want to solve for. So we're going to declare our ignorance, write that here. We don't know how to find it, but we want to know that we do want to find it, so I'm going to write it there. How about in the y direction? What do we know? We know that all right, now we can use this 30. You might want to say that delta y is positive 30, but you would be wrong, and the reason is This person fell downward 30 meters. Think about it. They started at the top of the cliff, ended at the bottom of the cliff. That means this person is going to end up below where they started, 30 meters below where they started. So this has to be negative 30 meters for the displacement, assuming you're treating downward as negative, which is typically the convention chosen, that downward is negative and leftward is negative. So if you choose downward as negative, this has to be a negative displacement. What else do we know vertically? Well, for a freely flying object, we know that the acceleration vertically is always going to be negative 9.8 meters per second squared, assuming downward is negative. Now, here's the point where people get stumped. And here's the part where people make a mistake. They want to say that the initial velocity in the y direction is 5 meters per second. I mean, people are just dying to stick this 5 meters per second into here because that's a velocity that you were given. But this was a horizontal velocity. That's why this is called horizontally launched projectile motion, not vertically launched projectile motion. So think about it. The initial velocity in the vertical direction here was 0. There was no initial vertical velocity. This person was not launched vertically up or vertically down. This person was just launched straight horizontally. And so the initial velocity in the vertical direction is just 0. People don't like that. They're like, hold on a minute. They're like, this person's going to start gaining, right? This person's going to start gaining velocity right when they leave the cliff. This starts getting bigger and bigger and bigger in the downward direction. But that's after you leave the cliff. We're talking about right as you leave the cliff. That moment you left the cliff, there was only horizontal velocity, which means you started with no initial vertical velocity. So this is the part people get confused by because this is not given to you explicitly in the problem. The problem won't say, find the distance for a cliff diver, assuming the initial velocity in the y direction was 0. Now they're just going to say, a cliff diver ran horizontally off of a cliff, find this stuff. And you're just going to have to know that, okay, if I run off of a cliff horizontally, or if something gets shot horizontally, that means there was no vertical velocity to start with. I'm going to have to plug this initial velocity in the y direction as 0. So that's the trick. Don't fall for it. Now you know how to deal with it. So we want to solve for displacement in the x direction. Look how many variables we know in the y direction. I mean, we know all of this. This is good. But we can't use this to solve directly for the displacement in the x direction. We need to use this to solve for the time, because the time is going to be the same for the x direction and the y direction. So once I find the time, I can plug back in over to here, because think about it, the time it takes for this trip is going to be the time it takes for this trip. It doesn't matter whether I call it the x direction or y direction. Time is the same for both the directions. In other words, the time it takes for this displacement of negative 30 is going to be the time it takes for this displacement of whatever this is that we're going to find. So let's solve for the time. Now, how will we do that? Think about it. We know the displacement, we know the acceleration, we know the initial velocity, and we know the time. Note that we don't know the final velocity, and we're not asked to find the final velocity. We don't want to know it. So let's use a formula that doesn't involve the final velocity, and that would look like this. So if we use delta y equals v initial in the y direction times time plus 1/2 acceleration in the y direction times time squared. All right, now we can plug in values. My displacement in the y direction is negative 30. My initial velocity in the y direction is 0. This is where it would happen. This is where the mistake would happen. People just really want to plug that 5 in over here, but don't do it. It's a trap. So 0 times t is just 0. So that whole term is 0. Plus 1/2. The acceleration is negative 9.8 meters per second squared. And then times t squared. All right, now I can solve for t. I'm going to solve for t, and then I'd have to take a square root of both sides because it's t squared. And what would I get? I'd have to multiply both sides by 2, so I get negative 30 meters times 2, and then I have to divide both sides by negative 9.8 meters per second squared equals, notice if you would have forgot this negative up here for negative 30, you'd have come down here, this would be a positive up top, you would have had a negative on the bottom, you would have plugged this in, you would have tried to take a square root of a negative number, your calculator would have been all like, I don't know what that means. And then you would have been like, I messed up. So you'd start coming back here probably and be like, let's just make stuff positive and see if that works. It would work because look at these negatives cancel, but it's best to just know what you're talking about in the first place. So be careful, plug in your negatives and things will work out all right. So if you solve this, you get that the time it took is 2.47 seconds. It's actually a long time. Might seem like you're falling for a long time sometimes when you're like jumping off of a table, jumping off a trampoline. That's usually like a fraction of a second. This is actually a long time. 2.5 seconds of free fall is a long time. So we could take this. That's how long it took to displace by 30 meters vertically. But that's going to be how long it took to displace this horizontal direction. We can use the same formula. We can say that, well, if delta x equals v initial in the x direction, I'm just using the same formula but in the x direction, plus 1/2 ax t squared. So the same formula as this, just in the x direction. Well, delta x is just dx. We already gave that a name. So let's just call this dx. So I'm going to scooch this equation over here. dx is delta x. That equals the initial velocity in the x direction. That's 5. All right, this is really 5 now. In the x direction, the initial velocity really was 5 meters per second. How about the initial time? Or sorry, the time. There's no initial time. The time here was 2.47 seconds. This was the time interval. The time between when the person jumped or ran off the cliff and when the person splashed into the water was 2.4. Let me erase this. 2.47 seconds. So 2.47 seconds. And this comes over here. How about this AX? This AX is 0. Remember, there's nothing compelling this person to start accelerating the X direction. If they've got no jetpack, there's no air resistance, there's no reason this person's going to accelerate horizontally. They maintain the same velocity the whole way. So what do we get? If we solve this for dx, we'd get that dx is about 12.4, I believe. Let's see, I calculated this. 12.4-ish meters. Okay, so if these rocks down here extend more than 12 meters, you definitely don't want to do this. I mean, if it's even close, you probably wouldn't want to do this. In fact, just for safety, don't try this at home. Leave this to professional cliff divers. I'm just saying, if you were one and you wanted to calculate how far you'd make it, this is how you would do it. So, long story short, the way you do this problem and the mistakes you would want to avoid are, make sure you plug in your negative displacement because you fell downward. But the big one is make sure you know that the horizontal velocity, the initial vertical velocity is 0 because there was only horizontal velocity to start with. That's not going to be given explicitly. You're just going to have to provide that on your own and your own knowledge of physics.